But there's some people that do that. They ride it out the whole way, and then just like you didn't get better.
It never got better. Yeah. All right, let's do it. All right, so today we're going to have a quiz, but it's all you have to do is sign this sheet today, and you get a quiz grade for being here today. So I just want to make sure it goes around. You got it? Everybody got it? Everybody got this? Sign in? Okay. You didn't sign? Here. Could you put on the top quiz? Just put quiz up there. Partial credit. Yeah, partial credit depends. Just showing up. What else was I going to say? Quiz. Oh. Juan, you want your test? Wrong folder. There we go. Here you go. Anyone else not get their test? Sorry. Yeah, just. All right, so easy quiz grade today. That's because I don't want to grade. I just finished grading today. And this is like from before spring break. I've got this pile of stuff. So this will be easy to grade. All right, so I wanted to start class with this example from 7.1. Remember, last class what we were doing is we were trying to find the area between two curves. And we had talked about you can have functions of x and functions of y. And I showed you at the end how you can use your calculator to actually graph functions of y. The reason I want to talk about this example was because the absolute value of x function appears. And I just want to make sure everyone knows how you would deal with that, like in terms of the graph. So let's act like we don't have that picture. And let's try and graph this. So when you look at the absolute value of x, it's a v, right? It's a v. But it has a more precise definition that I want to share with you, which is the reason I'm doing this problem. The absolute value of x is actually a piecewise function. It's two different functions. The first function is that it's just x itself. So if you plug a number into this, like let's say we plug in 4, it should spit out 4, right? So if I plug in 4, it should spit out 4. If I plug in 5, it should spit out 5. As long as it's a positive number, it's just going to spit out the number that you plug in, right? So we say that this function is equal to x if the x we plug in is greater than or equal to 0. Of course, if we plug 0 in, we just get 0 as well, right? But if we plug a negative number in, we want it to spit out the positive, right? So if I plug in -4, I want it to spit out +4. If I plug in -3, I want it to spit out -3. So I'm just going to do the opposite of whatever gets plugged in. I will do -x if I plug a negative number in, right? If x is a negative number, then I'm going to take the opposite of that negative number, and then it will be positive automatically, right? If you look at it this way, then you can draw the two pieces separately. This first one, x is the diagonal, right? It goes like this, f of x equals x. But I'm only going to draw it from 0 and then to the right. So I would start here at 0, and I would draw that diagonal like that. And then the other one, -x, is the same line, but instead of a slope of 1, it's a slope of -1, right? Because that's a -1 in front. And I would draw that to the left of 0, so that would be over here. And do you see that that's where you get the v from, right? The reason that's important is that when we're talking about what we did last class, right, where you have to figure out which function's on top and which one's on bottom, for us it's going to kind of matter where we are. Like if we're over here on the right-hand side, the top function would actually be x. And if we're on this side, the top function would be -x, right? They're two different things. Yes?
Is the reason why we do this is because we can't really do the antiderivatives or
Exactly. So you're reading my mind. The reason we're doing that is because we have never defined in this class what the antiderivative of the absolute value of x is, right? We have not defined what that is. We never talked about it, right? This is not 1/2 x squared because there's an absolute value around it. So the way that we get around having to worry about this, because absolute values make things pretty complicated. So to get around this, what we do is we realize that that absolute value is a piecewise function, and then depending on where we are, we can talk about the antiderivative. So yes?
Does the bottom portion of the piecewise function, does that need to be expressed as a limit?
No.
As it approaches 0?
Because this function is defined everywhere, right? It's defined at 0, and anything bigger than 0, and it's defined anything less than 0. Yeah. Now, if I didn't put that there, then we would have a hole, but we don't want a hole. We want, because the absolute value of 0 is actually 0. You could. It's not technically wrong to switch the two, because that would still give you the same thing, because -0 is still 0. They just can't both be. Well, you could actually both, because you both get 0, right?
That's true, yes.
So it wouldn't be wrong, just that's the normal way we write it, just like that.
So you were saying in respect to in the context of that,
Mm-hmm.
we're looking at the graph, you said we want the second quadrant, and it's the top, so you got it.
Yeah, let's draw the other curve here. Let's draw this other curve. That is a parabola that opens up, right? And it's been shifted down. So that looks like, I don't know, I'm just going to draw it in here. Parabola opens up, and it's been shifted down to, oh wow, that's not even close. Okay, there we go, there. Okay, so that's -2. Right, so if we want to define the region, or the area of this region bounded by the two curves, we're talking about this region in here. We want to know that area, right? Well, if we're going to do a type 1, which type 1 is the way we'd want to go here. Do y'all see why we'd want to go type 1? Type 1, our rectangles are vertical. And so with vertical rectangles, we always have a top function that is different from the bottom function. If we try and turn our rectangles this way, then we have a problem, especially right in here. Do you see that that's the same curve? So we don't want to go that way. We want to go this way. But as I move, let's say from left to right, as I move over here, the red function's on top, the black's on the bottom. Until I get here, then it's the blue on top and the black on the bottom. So I'm going to want to split this into two different integrals. Y'all see that? Now, I do need to figure out where these points are of intersection. So I would have to, let's find this one. How would I find that point? I would set what two things together? X, right, the blue one, x and x squared minus 2. So to find that point, I would set x, I'm using this one, to x squared minus 2. And then I move everything to one side. And then I factor. I hate using green markers because they're hard to see. And then you get 2 and -1, right? 2 and -1. And our answer would be 2, wouldn't it? Be 2. Okay. And then how do we get this one? This time we set -x equal to x squared minus 2, and then we work through this one. This time when we work this out, we're going to get -2 and +1, and of course -2 is our answer. Now there is some symmetry. On this problem we could, if we wanted to, just go from 0 to 2, right? And then double the answer because it's the symmetry. But it's kind of up to you how you want to do it. I'm going to do it as two integrals because I really want to illustrate again how you can still do these using the piecewise. So let me set it up. I'm not going to take this problem all the way. I'm just going to set it up for us. So I'm breaking it into two pieces. This one over here, okay, I'll call this area 1. That's area 2. So the total area is area 1 plus area 2. So area 1 is the integral that goes from where to where?
Is it -2 to 0?
-2 to 0, good. And then it's your top function minus your bottom one. Our top function here is the red, right?
Yeah.
which is negative x minus the bottom function, x squared minus 2, all of that dx. That is the area of the first region, right?
It should be A1 minus A2, right?
Here?
Yeah.
No, because I'm adding these two areas together, right?
Oh,
To-
okay.
I'm getting like the total area.
Yeah, okay. I thought it was somewhere else. Gotcha.
And then area 2 is going to be the integral that goes from 0 to 2, right? And now the only difference is our top function is the x, not negative x. The bottom function is still the parabola. So plus integral goes from 0 to 2, this time x minus then the x squared minus 2 dx. That make sense? Any questions on it? Of course, I would like distribute and all that, but that's a polynomial. It should be easy to find the antiderivative and plug in. Go ahead.
No matter which side you're on, it's the rank of -2, and 2 is on top on everyone, even though the still do the top versus the bottom, no matter what.
Yeah, always top versus bottom. Yeah, you don't. Even if both of these graphs were way down here, the top would be the one on top, and the bottom would be the one on the bottom.
Or since it's symmetrical, would you be able to multiply like just one half, do one side?
Yeah, that's what I was saying. If you wanted to, you could just go from 0 to 2, do that integral right there, and then double your answer. Yeah, with the symmetry, you could do that. But you got to be 100% sure it's symmetric. From the picture, it looks symmetric, so I think we'd be okay.
So does anything really complicated happen if you had a function that caused you to be horizontal rectangles, or is it just like the other problems for the most part?
Wait, what?
So like here we have vertical rectangles because we had the function x squared minus 2.
Uh-huh.
So if you had a function that made horizontal more ideal, would that drastically change anything, or would it be like kind of standard like the other ones before?
It would. I think it would be like the other ones, except remember on the horizontal we do right minus left, not top minus bottom. We do right minus left. The problem you would run into, I guess, is that in this problem, if we had absolute value of x, we're not going to be able to ever get that into a function of y. Like this is a function of x. It will fail the horizontal. So we'll have to do it as two different. It would be that's not going to happen. Yeah. I'm going to erase this.
Is there a time when you set it equal to 0 when you're doing some ambiguities between which one you want to change is the actual point that you're looking for?
Are you saying because we got two answers and one of them didn't work?
Well, just, I don't know, maybe there's a different problem that's more advanced, it might be like more complete. Maybe terms that are kind of close with, it might be.
You should be able to determine which of them works because you can always go back and look and plug it in and check it if you need to. You're not going to have anything like tricky where I'm like intentionally trying to make it bad for you, you know? Yes?
Is there a function in the calculator that you do quadratic simply and easily? I mean, I know how to
Do quadratic?
Right.
What do you mean do quadratic?
Quadratic equation. Like,
Oh, solve for it.
ABC. Because I mean, I can do it obviously, and I can plug it into the calculator in kind of a laborious process. But I didn't know if there was like an easy function where you just say, give me these three numbers. And you do that.
There is, but I forgot.
I mean, you can actually program your calculator to do that. You can, you know.
There was like a native.
Well, I think the easiest way to find x-intercepts on your calculator is to graph it and then use the 0 function of the graphing utility that actually goes and finds the x-intercept. That's probably the fastest way, cleanest way, other than writing a program where you just give it ABC.
Right,
And then it just does it, yeah. Okay, we're moving into 7.2, all right? We're moving into 7.2. We're finished with 7.1. 7.1 was about areas between curves, right? And now we move into 7.2, which is called volumes. And we have some preliminary stuff, some prelim stuff that we need to get out of the way first. Just some formulas that we all need to be comfortable with. If you take a rectangular box, right? A rectangular box, three-dimensional, like this, and you want to know what the volume of it is, then whatever this length is, whatever this width is, whatever this height is, we all agree that the volume of that's just length times width times height, right? There's no issues there. So that's the first thing. By the way, a rectangular solid box like this is called a parallelepiped. That's the mathematical name for that. Parallelepiped, I didn't make it up, okay?
I think the dress shirt box.
A what?
The dress shirt box.
A dress shirt box. Yeah, it could. But if the length and width are those proportions, it looks kind of like it, right?
I thought it was called a rectangular prism.
Well, there's other names. That's why parallelepiped is like the more mathy way to say it, you know? I mean, a lot of people just say that's a box, you know? I mean, but as long as we don't lose any, we need the parallel part, you know? And there's also, this is not like tilted, like nothing is tilted over. So it's not like you you have a square, or let's say you have a rectangle, and then you could have something like that too, right? These are right angles in here. All right, we're moving on. Length times width times height, volume. Okay, now, the next shape that we need to be comfortable finding the volume of is a right cylinder or a soda can. Now, this doesn't look like a soda can, but I'll draw it in a different dimensions here. I'll make it taller so it looks like that. If this is the height of the can and I give you the radius of the can, then the volume of this is pi r squared times the height, which is right here, right? Now, you may be familiar with this, you may not. It's kind of easy to see why this is the volume. If you think about pi r squared is the area of a circle, right? So this calculates the area of that top portion of our cylinder. And then the height, you multiply by the height, so you basically just multiply it times the depth of it, and that gives you the total volume. Okay? So is that all right? Okay. The next shape is a washer. Okay? So it's not as bad as it looks. It looks kind of bad, but a washer is basically a soda can where you cut a soda can out of the inside of it. So you got like two cans, a big can and a small can. So I'm going to draw that over here again, like this. I'm going to make this picture a little bit different, like that. So that right there, if I want to know the volume of this, what I can do is just think of it as being the big one, right? The big cylinder, take away the smaller cylinder that's inside of it. Well, they're the same height. That's not. There we go, right? So take the big one and then take that volume and then take out the smaller one from the inside. Same thing, right? So to do this, we have to have two different radii, right? We have to have what I'll refer to as the outer radius. The outer radius would be the distance from here to here, right? We'll call that R out. And then the distance from the center to here, call that R in. Those are two different numbers, right? Yep. And so the volume of this one, and they both have the same height, right? These both have the same height. If you're coming in late, you missed the quiz. You want to hand that over there? Anyone else? Yeah, okay. The quiz is just a sign-in today. Okay, so they both have the same height. So what is the volume of this one? So the volume of this one is pi times the radius, but the radius here is R out squared times the height, right? And then this one is pi times R in, that thing squared times the height. Same height, right? And so if I take that and subtract that, that's this right here, right? That's that times that, or that minus that. And then what did I do from here to here? I factored out a pi and brought it out front, right? And then I factored out an h and did it in the back, which doesn't make a lot of sense why I did it that way. But it's right, yes?
Does it matter?
Well, it's because of where I'm going with this, okay? So this is this, right? You could put the H out here, but just put it back here for where I'm about to go. So do y'all understand that now? Like this all makes sense? Volume of a washer? Okay. This is the last one, and then we'll be ready to get into the section. The last one is called a cylindrical shell, which is basically the same picture we just had. Yes?
Yeah.
Okay, but this one's going to be a little bit different. I'm going to approach it in a different way. All right, I'm going to approach this in a different way. Let me draw it here. I want to know the volume of this, okay? Let's say that this is H. Let's say that this from here to here is your R out. Let's say that from here to here is your R in. We already have a formula for this, right? We already do. But I'm going to do it a little different. What I'm going to do is I'm going to take my imaginary scissors, cutting shears, whatever you want. I'm going to cut this thing like that, okay? And so when I cut that cylinder, here's my cylinder. Of course, it has some thickness to it, right? But basic idea. Cutting it, I'm going to roll it open like this, and we're going to look at that instead. If I cut that and roll it open like this, then it becomes a parallel pipette, doesn't it? A box, right? That's what it becomes. Now, how tall is it? H. Okay, what is this thickness here? R out minus R in, right? That's this thickness, which is however big this was, take away the inside one, right? The only thing left for us to do is figure out how long it is. That should be the circumference, right? It should be the circumference of this thing, which if we open it up, right, that's the circumference, which is circumference, the definition of circumference is 2 pi r. 2 pi r, right? Now, which radius, though? R.
The addition of the radius?
Yeah, what would it be?
Because in order to get the r squared minus r in squared, you would multiply it by r out plus r.
Well, this is tricky, right? Is it R out? Is it R in? Is it an average? Right? What is it? So here, let me tell you what's going to happen. What's going to happen is eventually this shell is going to become infinitesimally thin. Okay, it's going to become, like we're going to take, just like we did with the rectangles, we're doing those, the area under curves, we're doing rectangles, but the idea is that these rectangles get more and more narrow, right? And they become almost essentially a vertical line. That's what's going to happen in this shell. This shell that has thickness is eventually going to become like infinitesimally thin. So this right here, I'm just going to put that this is 2 pi r, and I want everyone to understand that this r is going to be some radius that we will have to determine at some point. Like it's not r out, it's not r in, it's kind of like when they get sandwiched together, it's some arbitrary point in between those two. All right, so I'm just going to call it r.
So it's not the middle. There would be something there.
It eventually becomes the middle, but we won't even need that much. You'll see. It could be, that's what I'm saying, it could be R out, right? It could be R out, but there's a problem. What happens if I really cut this open? Like, I don't know think about this. If I really cut this open, is this really the shape? No. Yeah, these edges are not actually straight, they're curved because, well, you would have to physically do it, but if you open it up, it would not be, everything is perpendicular. Do you have a comment? Yeah.
Yeah, so like if you were to cut it open, the outside facing circle, like that becomes one face and now it'd be longer than the inside.
Exactly, your two faces would be different size. So I am doing this kind of loosely because I know that what's going to happen is I'm going to take a limit and this is really going to become like a really thin shell. And then if I look at it as a very thin shell, almost like a sheet of paper, then the outer and inner radius are essentially the same radius. If it's thin enough, right? Yeah.
Why can't you do R out minus R ends instead of that R? Because it would give you the middle, we're not necessarily looking for.
R out minus R in would not give me the middle. R out minus R in would give me that distance. You would have to have a point in between the two.
So you can't do divided by 2 either?
Well, that's different. You said subtract the 2. How do you find a number between two numbers? Do y'all know how to find? If I give you two numbers, how do you find a number right in the middle of them? Yeah, you take their average. So you could do that. Okay. So we could, if we want, do R out plus R in, divide by 2, which would be in
The
the.
other formula. Ultimately.
Yeah, but we're thinking too deeply about this because this is going to eventually become, like I said, this is going to be a limit problem. We're going to have a limit. And just like we've been working with rectangles, these rectangles in the limit become essentially like vertical lines, and we're adding up an infinite number of them. Same idea here. This shell, this shell-shaped cylinder thing eventually becomes like a sheet of paper shell. So the radius is just distance from the center to the outer edge. Let's just leave it at that.
And where does the rectangle go in the infinitely thin rectangle? Is it parallel with the circumference, or
I don't know what you're talking about. Rectangle where? This rectangle or that rectangle?
that rectangle you're pointing
Where does
at?
it go?
Yeah, like is it vertical? Is it horizontal?
Where are you talking about? Over there or over here? Like,
In comparison to the shell.
I haven't compared this at all to the shell. All I've said is that back when we're doing areas, the idea is these rectangles, and we have an infinite number of them, so they basically squash down to nothing or to a vertical line. Essentially, they're not vertical lines. Lines don't have areas, okay? This is in the limit. We have something that's approaching something, right? So here, I'm not sure I'm understanding what you're asking me over here now.
Okay. I can.
Yeah.
I can let it go.
Table it, yes.
Yes.
The circumference of 2 pi r?
Yes.
Which radius is that? Like for the r? Are we using the outer one or the?
That's what we're talking about. That's what we're saying. We're not going to complicate ourselves with which radius it is. It is a radius, right? It is a radius that when we do this thing thin enough, the outer and inner are going to be basically the same radius. So that's why I'm not calling it in or out. I'm just calling it R for now, and let's just, it's R is like something between here and there, somewhere in there, R, right? Somewhere in here, and it's going to get real thin, so it won't matter. Is that okay? All right, let's keep going. So, we didn't come up with a formula, shit. So the formula would be what? These 3 multiplied, right? These 3 multiplied. So it'll be, I think I have it in the notes. Scroll up. There we go. Uh-oh. Okay, so we have 2 pi h, so that's 2 pi h, and then what?
Times the top right, R out minus R in.
2 pi, what, I'm missing something up there, right?
You're missing the R.
I'm missing the r. 2 pi r. R out minus R in. That's the thickness, right? Yeah. I think that's a typo. I've not seen that typo before. Hold on. Let me move down. Okay, let's keep going. That should have an R in there. Not sure why it doesn't. Did I accidentally delete it?
It almost looks like it was converted to R out minus R in,
Yeah.
which doesn't make sense.
Yeah, that doesn't make sense. So let me just put it in here, there. Okay, we're moving on. All right, let me erase. Let's clear our minds here. All that was to establish a way of finding volumes of different geometric shapes, right? We can find the volume of a washer. We can find the volume of a box. We can find the volume of a cylinder. We can find the volume of a washer, and we can find the volume of a cylindrical shell. Those are the 4 things we looked at. Okay, so what are we doing? This is last class, right? We said, okay, give me some function of x on top, some other function of x on the bottom, give me a starting and ending point, find the area between that, we've got that, right? So today what we're going to do is we're going to take this picture and we're going to pull this out into three-dimensional space instead of on a flat sheet of paper. So we're going to look at it more three-dimensionally. And we're going to ask ourselves what would happen if you take that region and wrap it around the x-axis, just like this. And if you do that, you get this solid shape, right? And it's not a box, it's not a cylinder, it's not a shell. Like, it's nothing we just looked at. It's kind of its own unique solid, isn't it? And we'd like to know the volume of it, right? I would like to know, can we calculate the volume of that easily or not, right? So we need a way of doing it, right? Some things to point out here. If I take out the transparency and look at it this way, you might think from this picture that that's just like a drill, like if you just drill through, like it's a straight hole through there, but it's not, right? It is actually curved in there, so we have to be careful, right, that we account for the fact that the inside has that little kind of undulation. So we want to know, in general, if we have two functions, top one and bottom, can we take that region and wrap it around the x-axis and find a volume? Okay, so that's the goal. How do we do it? Let's see. The approach here is going to probably surprise you, like how easy it's going to be in terms of like the calculus idea. The integral is a very powerful tool now for us. The integral adds things up, infinitely many things. That's what the integral, I want you to think about the integral that way. It's a sum, but it's a special sum where you're allowed to have an infinite number of things in there that you add up. So let's take some region bounded by two functions here. Say that's A, that's B. And I want to wrap that around the x-axis, okay? So if I wrap this around the x-axis, what I normally would do here is I draw like a curved arrow and then a curved arrow like that. And that lets you know I'm wrapping this whole region around the x-axis. And we just saw on the computer what something like that might look like, right? It's hard to draw that ourselves. Yes?
So the x-axis is the center of our solid?
In I guess in one direction, yes, you could say that, right? Because the center is a point, right? It's a point. You rotate. So we call this x-axis the axis of rotation, okay? So our x-axis is the axis of rotation. The way we get it, the way we can figure this out is to break it up into smaller pieces. I should have shown you this first. Where's my other? There we go.
Intuitively good at calculus?
Say it again.
Does this mean that people who do pottery are just intuitively good at calculus?
They are by definition incredible at calculus. No, I have no idea.